This rigid steel frame is located at our F4 building, and I think you guys already have a chance to take a look at it because we have the some lab over there. But if not, if you still at SUT, just come to see this steel rigid frame. This steel rigid frame is used for the test of the development of precast reinforced concrete beam in our lab for our master degree student Pichuto by using the 4-point loading test. And based on this, if you take a look, we have the steel loading frame. We used to have the load cell over here, and when you put the load into this transfer beam, that load will react back to the steel loading frame. And based on this, if you take a look at this, we have the support over here, which is fixed support at both sides of the frame. Okay, and also we have the joist over here is a kind of rigid joist. This kind of detail of construction, we can assume the fixed support and the rigid joint. When this frame subjected to the load, what happened is you must model this frame, okay, based upon this. You may set the frame that we have here may have this beam, and this beam connected rigidly with this steel column, and the steel column is a little bit long because we can change, adjust the tallness of this beam easily, and then by putting together you may get this kind of model. Okay, and based on this model, you got to talking about the rigid joint and the fixed support, and under this is subjected to the load here. Okay, by looking at this frame is in symmetry, and the deformation of this frame will be in symmetry also. Okay, and if for somehow the loads just change the position, not at the middle of this frame, but when is subjected to the load outside the symmetric axis, such as this one, this frame is not in symmetry. So typically we separate the beam into the one is not symmetry and another one is symmetry. What the difference is? The symmetric frame, symmetry. The symmetric frame can be considered easily. For example, if I just take the tall column out and model this frame to be the one like this, under the application of the symmetric load on the symmetric frame, what we have is, let me put it in the downward direction so the conservation is going to be easier. And what we have is the deformation of the frame will be in symmetry. By doing that, what we have is the deformation of this frame, will be something similar to this. And then over here is we'll keep the 90-degree angle, and it's also keep the 90-degree angle since the joint is the rigid joint. So the deformation of the structure will be in symmetry. Okay, and then the degree of freedom of this frame will be, let's say this is A, this is B, this is C, this is D. We will have only theta sub B. And since due to the symmetry, theta sub b is going to be minus theta sub c. We will be talking about this frame later. And this kind of frame, which has symmetry, has no sidesway. Okay, has no sidesway. And the analysis of this frame will be spatial, very similar to the analysis of the beam. Okay, but for the beam that has the non-symmetry, for example, for this one, if I reduce the complexity of this problem into the frame like this, okay, and let me adjust the load to be the downward one so you guys can understand it easily. What we have is the deformation of this beam will not in symmetry, and then it will have sidesway. Okay, even though the structure is in symmetry, but when the loading is not symmetry, this kind of frame will have the sidesway. What happens is, if you consider the fixed end moment due to the application of the force, and by assume the load at close to this point, we will have the fixed end moment, the black one, larger than this light blue fixed end moment. When the fixed end moment on this point B is larger than the fixed end moment of this point C. So the distribution of the force may cause the deformation of this one to be something like this, have some sidesway. And then due to this, the elastic curve of this one will be something very similar to this, in which we still have the normal angle at the joint B and joint C. Okay, and what we have is the analysis of this frame will be more complex, since the degree of freedom of non-symmetry frame going to be what? This one going to be theta sub b, theta sub c, and also the delta, three of them. Okay, and when you compare this one with the degree of indeterminacy, what we have is going to have equal to 6, 3 plus 3 minus 3. So this problem, you will have 3 degrees of indeterminacy. And based upon this, in the analysis of the fourth method and the displacement method, going to require you to solve for 3 is unknown. Okay, and for the scope of our teaching, okay, the column may not be equal. For example, the frame is like this. For this one, this frame is not symmetry, even though the frame subjected to the symmetric load. Okay, this frame also has the sidesway. And then I should tell you that the scope of this course, first, we will have this kind of frame. The second, we will have this kind of frame. Okay, and then let's move to another steel rigid frame. You may see this kind of rigid frame in the port, okay, near the seashore, such as the one in Hood. And this frame usually can move, and you may consider this joint, this support to be the pin support, and then the model of this frame will different from the previous one. So now our structure will have the pin support, and then if you consider, for example, the point load due to the crane machine over here, you may put the point load like this. And then if you also include the uniformly distributed load, you may also put this kind of self weight of the girder into this frame. What we have is this one will have the degree of independency of 4 minus 3 and then is equal to 1. And under the application of the force, since the moment on this A, B, C, and D, the point C is larger than B, and I believe this frame will have this kind of deformation, and then it's going to keep the angle here in the normal angle, and also since the joint is the rigid joint, this one going to keep at the 90 degree. So the degree of freedom of this one will be zeta sub A, zeta sub B, zeta sub C, zeta sub D, and also delta. So if you solve this frame by using the force method, you're going to have the total of 5 degrees of freedom. But if you solve it by using the force method, you have only 1. But anyway, when you solve this kind of problem, you can reduce, okay, basis upon the slope deflection, or even though the moment distribution, you may use for the moment distribution, you may use this one as the 3EI over L, and the beam for the 4EI over L, and for this one is 3EI over L. Okay, by doing this, you can reduce the zeta sub A and the zeta sub D. The degree of freedom will reduce to only 3. Okay, if you use the slope deflection, this one 3EI over L also, this one also, but for the slope deflection, the equation could be 2EI over L for this side. So anyway, this kind of frame has limited constraint. So when you change from the fixed into the pin, the force method going to be easier to use to solve this problem. But anyway, you got to use both force method and this pin method. You have no choice. And what else do we have? If you consider this one, you also possible to have the frame have unequal column like this. So I like you guys to have chance to practice this kind of frame. Okay, and basis upon this again, if you do the moment distribution, this one will be 3EI over L, and this one 3EI over L, and this one going to be 4EI over L. When you go back to this one, this frame only have only one choice, 3EI over 4EI over L, 4EI over L, and 4EI over L. The problem is, if we have the mix between this kind of support, for example, one is fixed, another one is pin. Okay, by doing this, you're going to consider the problem clearly. This one will be 4EI over L for the moment distribution. This one will be 4EI over L, and this one will be 3EI over L. And again, the problem can be equal column and unequal column. And I like you guys to have a chance to practice, okay, to solving this kind of frame. One is the frame with equal column subject to unsymmetrical. And another one, even though the frame is subjected to the symmetric load, but the frame itself is not in symmetry. This one also has a sidesway. Okay, and then that's fixed. You may have fixed pin or pin fixed whatsoever. And the last one, you may have the problem with the pin, equal column and non-equal column. That's going to be the scope of this second part of moment distribution. And I like you guys to do this kind of practice. Practice of what? We call this one the first part of analysis of the problem in order you to analyze it and select a proper K, which is the proper member stiffness matrix. Oh, sorry, member stiffness factor, member stiffness factor. And it's important because when you compute a correct case, okay, you will need it to compute the what's so-called a fixed end moment. And based on this, you also need to compute what is the degree of freedom. If you compute the wrong case, the DF will be wrong. And the fixed end moment is dependent on which one you select. If you use the 3EI over L, your fixed end moment will basis upon this kind of fixed end moment. And if you select for the 4EI over L, your fixed end moment will be here. Okay, so the analysis of the problem is very important, such as you put correct button, your shirt will be nice. Okay, if you put the button wrong, everything later will go wrong. So this is the first part of this. I like you guys to start by concentration on this. Next, let's come to the frame with no sidesway. I suppose to tell you that this analysis is equivalent to the analysis of the beam. When the frame has the support such as the fixed support, when it's subjected to fixed support, let's say this is going to A, B, and C. Due to the fixed support, you guys know that the slope at theta C is 0. The delta Cx equal to delta Cy equal to 0. There is no deformation. Okay, and based on this, what is so-called the sidesway is the linear usually is linear displacement to the left or to the right. Okay, and based on this, you have delta sub Cx constant. So there is no sidesway if you have the fixed support. And then consider this, you have this one as the pin support. Okay, at the pin support, let's say this is going to be the point A, B, C, D, and E. And you may have the theta sub A won't be 0 due to the rotation over here. But the delta sub AX equal to delta sub AY equal to 0. In this case, this frame also has no sidesway. So the first thing, if the frame has the fixed and the pin support, okay, the frame will has no sidesway. Okay, and the next one, if the frame is in symmetry, like the one that I draw to you guys before, such as this one. Okay, this one will be the frame with no sidesway due to the symmetry of the frame and the symmetry of loading. So there is two types of frame with no sidesway. Okay, and if you come to analyze for the problem, you may have the degree of indeterminacy of this one to be 6 minus 3 and is equal to 3. And if you do the analysis of the degree of freedom due to the fixed support at A and C, so the degree of freedom going to have only theta sub B when there is no axial deformation of beam and column. Okay, and you can see based upon this frame has fixed support, the displacement method of analysis is going to be very powerful for this one. Coming into this one, what is the degree of indeterminacy? A pin, D pin, E pin, so it's going to be 6 and then minus 3. So this one is going to have 3 degrees of indeterminacy. And for the degree of freedom, you may have zeta sub A, zeta sub D, zeta sub B, zeta sub C, and zeta sub E. That is going to be 5 of them. Okay, and when you compare this for this frame, the force method is going to be easier to use. So it's only for 3 unknown. But if you consider this frame deeper, you may say, if you use this one for 3ei over L, this one for 3ei over L, and this one for 3ei over L, so you don't need to consider zeta A, zeta D, zeta E. So you have only two degrees of freedom left. So the method, the displacement method, is going to be easier to use compared to the force method. So it depends how you analyze the frame and use the equation. And for the moment distribution for this frame, is going to be very convenient to use this one. However, for this one, you have no choice. You always have use 4ei over L and 4ei over L for this problem. So the analysis procedure, the same thing. You start by consider the given frame and select the appropriate member stiffness factor. That means you got to select a proper K. Okay, if the far end is fixed, you always use this one. Or when you consider the member of the frame or on the beam that's inside or inner the structure, you're going to use the 4ei over L. However, when your structure has the far end as the pin or roller also, you can use 3ei over L. And then based on this, you got to compute the distribution factor. That means if you compute the correct K, you will get the correct distribution factor, because it's going to be the stiffness of the member divided by the total stiffness of the joint. And again, if you consider the pin, the distribution factor is going to be 1. Why is going to be 1? Because the pin can take no moment. The moment at the pin is 0. That means there is no moment at this one. When moment come to the pin, they just distribute out the total of them. So the distribution factor is 1. Opposite to this, you may consider the fixed end. How come the distribution factor to be 0 for the fixed end? Because the fixed end take all the moment that come into the fixed end. No distribution. That means no distribution. So when you have the moment of 100 times 0 is 0. So you may call this no distribution of moment. Okay, and then coming to the fixed end moment is depend on what kind of K you use. For the typical K, general K, you may use the fixed end moment like this. But for the 3ei over L, you must use this kind of fixed end moment. And then you may do the moment distribution as you have the skill for the beam. They are going to be the same. And then draw the free body diagram, draw the shear diagram, draw the moment diagram, and draw the elastic curve whatsoever. This is going to be very close to the beam. Okay, let us start to this frame. Again, this frame has the fixed support at point C and point D. So this frame will has no sidesway. Okay, and the analysis is going to be similar to the beam. And based on this, if you consider the frame has the cantilever portion, and as you know, if you have the cantilever portion, you can determine the shear. okay, at this cut to be 36 kilonewton, the same as the applied force. And also you will have the end moment to be 36 times 1.5 kilonewton meter. And then you can draw the shear diagram, you can draw this is going to be downward and upward, and you can draw the moment diagram of this portion easily. So by doing this, you may just take this portion of this frame out. How many degree of indeterminacy of this frame? This frame going to have the degree of indeterminacy of 6 minus 3 is going to be 3. And how about the degree of freedom? If you take the portion AB out, so the degree of freedom going to be only zeta sub b. So this problem going to be easier when you use the displacement method to analyze it. Again, the frame has overhanging member AB, okay, and you can analyze this portion separately by using the free body diagram and equation of equilibrium. So we will simplify this one by using a proper one. Again, this one very close to what we have in the beam. Are we going to use the same method to analyze it? No. For this kind of frame, okay, and when you consider what we have the example for the beam, if you remember our beam, we have the cantilever, but what we have is the portion of the cantilever is connected to the roller support. Okay, so by doing this from the previous example, you may use the 3 EI over L for this portion. But our cantilever for the frame, our cantilever connected by 2 members. So by doing this, it is not the external. It is not the external roller, it is the member. So we are going to use 4 EI over L here and 4 EI over L here. So the way we consider this problem is different from the way we consider this beam in the previous lecture. Okay? Okay? And by the difference of 3 EI over L here and 4 EI over L, we will consider like this. So for the member BC, okay, that's going to be 2 EI. The stiffness is going to be 2 EI. So it's going to be 8 EI divided by 5. And when you consider for this column, it's going to be 4 EI over 5. And you can see this time, this beam is stiffer. This beam is stiffer than the column. Okay, and this portion going to have higher distribution factor compared to the BD. Okay, so we come to the next one, the distribution factor. Since this one is C, it's going to be distribution factor CB. Since this is fixed and this one going to have distribution factor of 0. Okay, and this one will have distribution factor DB. And again, this is going to be 0. So we move to this one. This one going to be the distribution factor BD, and it's going to be the K sub BD, and then divided by K sub BD, and it's going to plus K sub BD, K sub BC. Okay, so you have this one for 8 over 5, and then divided by 8 over 5. Plus 4 over 5, and then you may get this one to be 0.6667. Okay, and then if you know this one is 0.6667, 666. The distribution factor for BC is going to be 1 minus 0.6667. It's coming 0.333 and 3. Okay, next one. The distribution factor for the fixed NCD is they are 0. And distribution factor BC is over here. You see, BC. That is correct. No, BD is 4. Sorry, this is 4 over 5. 4 over 5. And then this one is going to be 0.3333. And this one going to change from this one to 0.6667. Why I know this? Because the beam going to be stiffer. When the beam is stiffer, BC is stiffer, the distribution factor of the beam must be larger. Okay, over here, the yellow must be larger than the light blue. So the BC is going to be here. It's going to be 0.667, and the light blue going to be the what? 0.333. And then fixed end moment. Since you use 4EI over L, fixed end moment going to be fixed weight. It's going to be WL square over 12. And before that, we come into this one. And then when you consider this moment, we have this one for 36 times 1.5. And it's going to be positive kilonewton meter, right? This is going to be positive. And then coming into the beam BC, you have the fixed end moment BC, and that is going to be negative because this one is in the counterclockwise direction. So you have this one for minus 135. And then for the fixed end moment CB is going to be positive 135. Okay, so come to the table. Before we go to the table, let's talk about the fixed end moment at this one again. We consider to be the external moment as one shown in the example T dash show. Okay, and the K factor in this is going to be 4EI over L. Why? Because it's connected by the member. It's not connected by the roller as the overhanging member for the previous lecture. Okay, that's U3I over L. And then by doing this, just put everything together. Okay, CB is going to be at this one, CB, and also this one is going to be DB. This is DB, not DC, DB. Please change it, okay, for me also. And then we have this one for BA, and then we have this one for the BC, okay, and the last one you have for this one for the BD, okay, and then consider the fixed end moment that we have, okay, and we have the fixed end moment for this one. This is fixed end moment BC, okay, that is going to be negative, okay, and another one, this one is going to be positive. And then coming into the choice B, the choice B that we consider has 3 of the member, and you can see the moment is not in equilibrium. You may require it another plus 81, okay, to make it in equilibrium. When 81 come from, it's going to come from time this one and take down this one. You're going to have this one for positive, okay, and you time this one going to downward, this one going to be in the positive. So these 3 moments must be in equilibrium. We require the 81, and 54 come from BC, and 27 come from the BD, come from the column. This one come from the beam. And then you see, this one gonna have 27. This one will carry over into this portion. The BC gonna carry to CB. So this one will carry over here and reduce by half. And this one will carry the 27. The 27, we have 27 over here. And then it's going to carry over to this one. So it's going to be reduced to 27 and 13.5. And this moment going to distribute further? No. This is going to be required 13.5 to make it in equilibrium. But when it's time 0, this one will drop down to 0. All the moment absorbed by the fixed support. The same occur for the moment in this portion. 27 was absorbed by the fixed end moment and take it to be 0. So we end our moment distribution, and then we can sum the moment. And also, if you consider the moment at point B, they are in equilibrium. Okay, and then you use the end moment and draw the free body diagram of the member of the frame, and later you determine the fixed end shear of all the member, and later you can draw the shear diagram and moment diagram and the elastic curve. And be careful, the rigid joint still always has the same rotation. What I mean is the rotation of the column here, the rotation of the beam here, and again the rotation of this portion on of them is going to be zeta sub b, and this zeta sub b rotate clockwise. Okay, and can you determine zeta sub b? Yes, you can determine zeta sub b by using the slope deflection equation, and I'd like you guys to do so. Okay, just use the slope deflection equation. What is going to be the zeta sub b? You may use m sub bc, okay, to determine it. M sub bc is going to be this one for the slope deflection, 2ei over L. Okay, if you can remember, the L of this one is going to be 5 meters, and moment here is going to be m sub bc. M sub bc is going to be minus 81. Okay, so this is going to be minus 81. This one is going to be minus 81, and this is going to be 2ei. It's going to be BC, right? BC, yeah. 2ei over 5 and 2 zeta b plus, this is 0, this is 0, minus 0. And if you remember, we have the fixed end moment here, positive 135. Okay, that is positive 135, right? Okay, you have this one. Have this one is BC. BC. This one, another one is going to be BD. Okay, that is minus 31. And then fixed end moment. You have fixed end moment of what? CB. Oh, that's wrong. You got to use the BC. The BC is 135. Okay, that is wrong. This is going to be minus. Sorry. This one going to be the minus 135. The fixed end moment over here, minus. So what we have is going to be, this is going to be plus 135 minus ST1, and then it's going to be 2ei over 5. 2 times 2 is going to be 4. Okay, so this is going to be zeta sub b, and your zeta sub b is going to be 135 minus 81 times 4 minus times 5 minus 4, and then this is going to be the EI. Okay, and then this is positive. That means it's going to be the clockwise direction. Okay, and I leave this one for you guys to do the practice by yourself. Next, we come to the frame. This frame is special. Again, there is no sidesway. This frame is in symmetry. Okay, is symmetry of what? Symmetry due to the shape of the frame, and symmetry due to the loading. Okay, by doing this, if you consider this one, the degree of indeterminacy is going to be 6 minus 3. That is going to be 3 degree of indeterminacy. However, for the degree of freedom, you have zeta sub A is 0, zeta sub D is 0, and you will have zeta sub B and zeta sub C. And since symmetry, the delta is 0. And if you can imagine, the deformation of this one will be something like this. Okay, due to the symmetry, it is going to be deformed like this. And due to the applied force here, as we lectured before, the angle here is going to be in the normal, and then this one going to be concave downward. Okay, and then the other one here going to concave upward, and then what we have is the symmetry of this wave as we show. And if you see this, you can look compared to the ankle that's rotated, okay, like this. So this is going to be zeta sub b, which has the direction clockwise. And if you consider for this one, okay, and you can see the rotation of this is going to be counterclockwise, and they are going to be the same. We are going to have zeta sub b equal to minus zeta sub c. This is the analysis of this problem. So the frame is symmetry. Degree of indeterminacy is going to be 3. Degree of freedom is going to be only 1. Okay, and then you will analyze this frame only by half of it. Okay, so by half of it, what is mean you're going to use this one for 4EI over L. And due to the symmetry, for this one, the K is going to be 2EI over L. Okay, we have this. And then the members, the factor for the column AB, 4EI divided by 4 is EI. However, for the beam, it's going to be 2EI over 4. And you can see the beam now has only half of the stiffness of the column. So the distribution factor of the beam here will be less than the distribution factor of the column here. That's the meaning of what we have for the number here. And then we go further, the distribution factor for the fixed distribution factor. For distribution factor AB is going to be 0, and it's going to equal to distribution factor DC. Okay, the fixed end. And then you go to the fixed distribution factor for the BA. It's going to be BA is here. Okay, the stiffness of this column divided by the summation of the stiffness of column plus the stiffness of the beam, and then you get this one for 0.667, and for this one just 1 minus 0.667, the distribution factor, the yellow one, going to be 0.3333. So the fixed end moment, this is the uniformly distributed load. the fixed end moment going to be WL square over 12. There is no fixed end moment for the column AB and column CD. Only fixed end moment BC 2 times 4 square divided by 12. Okay, and then you got this one. Only use this one for BC. Counterclockwise is going to be negative. And then you get this one for negative 2.667. Come to the distribution table again. We are going to work only half of the frame. Okay, and then AB is 0, BA and BC. Now we have the fixed end moment of minus, okay, 2.667. And if we consider the equilibrium of this joints B, okay, we require to have positive 2.667, and this 2.667 positive come from time this one take down 2.67 times 0.3333. Actually maybe plus 2.5, we require plus 2.667 times this one and take down this one, times this one and take down this one. You get the positive, okay? And then when this positive 0.889 and positive 1.77 come, this one gone. And then what we have is the flame is in symmetry, okay? And this is not done yet, okay? This is going to be what for the column AB and BA. For this one, you have what? You have this fixed end moment of 1.778, and you have this one for 0.889. And this table is not complete. You're going to carry over this one to this one. So usually this one will be carry over moment, and then this is going to be 0.889. Okay, that is going to be carry over moment. And since this is going to be in equilibrium, is required minus 0.889, and 0.889 minus times 0, and this one going to be 0. So we end our computation, and what we have is this is wrong. We're going to have this one for 0.889. Okay, positive due to the carry over moment. And then this one going to be 1.778, and another one going to be minus 1.778, and then you get this one. It's going to be something wrong. This is going to be 0.889. Okay, and now what we have is the moment that you can determine. This is positive, right? So this is going to be 0.889, and this is also positive. So it's going to be in the clockwise direction, 1.778. This one negative. Okay, so when it's negative, it's going to be counterclockwise, and this structure has the uniformly distributed load like this. And then for the symmetry, so this one is going to be 1.778 like this. And then what we have over here, okay, for this column, you're going to have this one for 0.889. And then you got to determine this is clockwise, so you're going to have this one we call A sub x. And also this one in this direction, you can also determine this. I cannot remember the A, B, C, and D. This one is going to be D sub A. Okay, and based on this is 2 kilonewton per meter for what? For 5 meter. If I'm correct, it's going to be 4 meter, sorry, that is going to be 4 meter. So this is going to be 4 times 2 is 8. And due to the moment cancel each other. So what we have here is going to be the force of 4 kilonewton. And this one also 4 kilonewton. And this one will transfer to here and transfer to here. This one going to be 4 kilonewton. And this one also going to be 4 kilonewton. And this one is kilonewton meter. So what we have is you can determine what? You can determine the reaction of the frame, okay, at support A, and also the reaction at the support D. And then this is another thing I supposed to tell you to determine the reaction of the frame, okay. And later you can draw the shear diagram and moment diagram. And then what we have for the A sub x, summation of the moment at B equal to 0, you will have for A sub x, is equal to 1.778 plus 0.889. Okay, and then you may have A sub x equal to, put it into your calculator, 1.778 plus 0.889, that is going to be 2.667 divided by 4. It's going to be 0.667 kilonewton. This is going to be 0.667 kilonewton, and believe me, this also 0.667 kilonewton. And then this is going to be, there is no force. This is going to be 0.667, and also for this one. So you draw the shear diagram and moment diagram, and to be complete on this, please specify of this, the column has no uniformly distributed load. So the dV by dx going to be 0, okay? And then for the beam, you have what? You have 2 kilonewton per meter. So you get this one and this one, the dV by dx equal to -2. Okay, and then you got this one to be 0. So when you recall back 0.889, if you use the sign convention for the instatic, 0.89 going to be positive. Okay, and then if you use this one for the sign convention, this light blue going to be negative. Okay, this one going to be positive, and this one going to be negative. And then for this one, the dm by dx going to be minus 0.667. This one going to be minus. Okay, and then if you go a little bit further, draw the sign convention for the electrostatic. See the yellow and the 1.38 go in the same direction, equal to 0. So this one going to be negative. Okay, so you have this one for the negative. And then if you go in further, come here, use the same sign convention. This one also negative, and this one also negative. So you have negative moment. And how come this one? What next is, don't forget about the slope here. The dm by dx is going to be this one, plus 4. How about this one? This one, the dm by dx going to be this one, minus 4. This one, the dm by dx is going to be 0. So where this come from? Okay, the moment here, minus this one, minus 1.778, and then it's going to be equal to area here, 1/2 of 2, this is 2 meter, and then times 4, cut. So um is going to be 4, this one minus, and then plus, and then move to another side 1.778, and then you get this one for 2.22 kilonewton meter. So I let you guys to go and make this one as complete as possible and come into this. Okay, you know this one is negative, right? And then this one, the dm by dx gonna be positive. Positive what? This one positive 0.667, and then it's going to be positive. And then the moment here is going to be 1.77 since the slope here is positive. Now you have what? You have the deflection. This one concave upward, this one concave downward. Okay, this one will concave something like this. Okay, and then it's going to rotate like this. And again, this one also, this one will has the rotation like this, and then rotate its back. And for this one, it's going to keep the normal angle, and this one concave downward, concave upward, and then you have this one for the elastic curve. Okay, there are 4 inflection points as indicated here. Okay, that's all for the frame with no sidesway. We come to the problem with the frame with sidesway. The frame with sidesway always occur in many kind of typical structure. Okay, when the structure, even though it is symmetry, but that structure is subjected to the lateral load. It may be come from the wind load or the earthquake load. This frame also has the sidesway. Or even though the structure subjected to the symmetry load, but the structure itself is not in symmetry, such as for this one, the frame also has the sidesway. Okay, and based on the frame with sidesway, the problem is our formulation for the moment distribution, we didn't consider how the structure has the delta deformation like this. We didn't consider the deformation delta. Okay, for example, if we consider for the column AB for this problem, okay, and you can see this problem also has the delta. When we consider by the moment distribution, the theta sub A gone, this one gone. Okay, this term we didn't put it into the consideration, and that is the limitation of the moment distribution. That happened. So we got to do some modification to the moment distribution in order us to taking care of the sidesway. Okay, and how to do so? Professor Henry Cross proposed that we are going to use the principle of superposition. Separate this beam into 2 cases. One is going to be the case that the structure prevent from sidesway. When you prevent sidesway or we has no sidesway, the problem can be analyzed by the moment distribution. By doing this, an artificial joints apply to the joint C to prevent the sidesway. Okay, under the application of the loading, we are compute for the fixed end moment due to this one, and then we do the moment distribution. You get the M sub O, and then we compute for the reaction R. Okay, we will be talking about this later. So we will have the reaction force R. This reaction force supposed to apply to the structure. Okay, let me stop here. Again, let's stain the frame at joint C and find the end moment M supernode here, and find the reaction R. Okay, the wording here can put simple like this, and then coming to that, we can apply the bus. But what happened is the frame has the sidesway. When we don't know how much it occurs for the delta. So even though we apply the R into this structure, but the fixed end moment due to the sidesway over here, we cannot compute. So what we can do is we must assume what? Assume the fixed end moment that act on this structure. Okay, and then we do the analysis for M palm, and then we find the R palm. This is not going to be the R, but it's going to be the R palm. And then by the principle of superposition again, and we consider the force at joint C. So this is 0, the joint C, and equal to this one going to be the R in this direction. And this one is going to be in the opposite direction minus R palm. And since this one is assumed, okay, this R palm cannot use in this equation directly. It must be modified by C palm. And in this way, we can compute C palm equal to R, okay, R, which is here, and then divided by R palm, which is going to use to apply here, okay, and then what we have is the moment M palm here will be modified to be C palm and then M palm. And the problem of finding the moment here is now readjust. And again, we will have the moment occur in this one equal to the moment here M super naught. And then it's going to be plus what? Plus C palm, M palm. And now you're going to get the moment that you would like to determine. So this one again, we cannot use R directly. We may put it into the R palm by assume the sidesway, okay, or assume the fixed end moment, okay. And we said you may assume two things. You may assume the delta, okay, or you may assume the fixed end moment, the more convenient. And I will do it in the examination. I will assume the fixed end moment. Why we do so? Because we know from the fixed end moment that the fixed end moment for this one, fixed is going to be 6 EI delta divided L squared. If you assume the delta, you still need to compute the fixed end moment. But if you assume the fixed end moment, you get this one directly, and you can do the computation for what? For the M palm. Okay, easier. So we will assume the fixed end moment of the column and find the end moment M palm and then R palm, as I show over here. And then you adjust, you put into this one to have the correct factor to adjust the M palm. Okay, by doing this, what we get is C palm equal to R divided R palm. And then the moment M equal to M super naught plus C palm M palm. So that is the whole thing. The next two slides explain you how should you assume for what? First, for the sidesway or for the fixed end moment. As I said, it's going to be more convenient to assume the fixed end moment better than assume for the sidesway, because if you put everything into the equation, you going to do some computation to get the fixed end moment, okay, by this equation. So it's better you don't need to assume this one, just assume the fixed end moment directly. It's going to be easier to do so, okay. That is what I like to speak over here. So follow what I did. We will assume the magnitude of fixed end moment directly. Okay, and then later you may also put the fixed end moment here, and you can determine the sidesway if you prefer. And then the delta is going to be C palm delta palm. You will get the actual sidesway by putting the delta palm by assume fixed end moment by the correction factor C palm. Okay. We're going to modify a lot of things. We're going to do a lot of modification for the frame with sidesway. Now, as you may conclude, we're going to do moment distribution 2 times because the frame is going to be separated into 2 cases. Okay, it's going to be separated into 2 cases. Before you can separate the frame into 2 cases, you got to analyze the problem. You got to analyze the problem because your problem can be this one, can be this one, and the support of this frame can be classified into 3 of them. One is going to be fixed. Okay. Another one is the pin, and pin. Another one is going to be pin and also fixed. Ajahn, can you change the pin to the roller? For this one, I can do more if I prefer, but usually we don't just put this one into the fixed, and this one gonna be the roller. This also be the problem that we can solve, but this kind of problem gonna involve a lot of things. So just do what we have on this portion. We will limit our consideration to the problem like this, and I may put the hinge into it. That is also possible, like the one that we have in the second examination. Okay, we limit our concern to these problems. Okay, and when you analyze the problem and basis on this, you got to select the member stiffness factor. Okay, generally we use 4EI over L. For the for the pin end or the roller end, you use 3EI over L. Again, the same as the first case or the second case. You're going to use the same K. And this K you're going to use to compute the distribution factor. This distribution factor will be used for these cases. So it's a requirement. You're going to do it very carefully to get this distribution factor correct. Your computation will be correct again. If your problem is going to be pin, okay, the pin end, the distribution factor gonna be 1. And if your end is going to be fixed end, the distribution factor gonna be 0. What the physical meaning of this distribution factor 0 and distribution factor 1? If you cannot explain it, go back to the start of this PowerPoint. I did explain it before. Okay, and then you do the fixed end moment for the case 1. Okay, and you do the same as you did for the frame with no sidesway. The same. This is the same as the beam. The frame as the same as the frame with no sidesway. Okay, so that's why I will not give you the examination with the frame with no sidesway because it's a part of this problem already. Okay, and the problem on the third examination for the beam, the score will be less than the frame with sidesway. Okay, there is two problems. One is beam, another one is a frame with sidesway. And then you do what? From the fixed end, okay, from the fixed end, you extend it, give it no sidesway, fixed end, you determine M sub O. And then for sure, you will determine the reaction R, okay, that's used to prevent the sidesway. And then you finish it. And then you finish it. You go to the second case, you just assume the fixed end moment. For example, 10 kilonewton meter, 100 kilonewton meter, I will give you the fixed end moment in the examination. So everybody will obtain the same fixed end moment, and the solution that you solve will be the same. So it's going to be easier for me to grade your examination, okay? And then for this fixed end, you move a little bit further to determine the M palm, okay? For this fixed end, you compute the M palm, and for sure, you will compute the R palm. So you get the R palm, okay? And then this is going to be another end. And then you compute the C palm. C palm equal to R over R palm. And then you make the correction to the M palm here, okay? And later you put the C palm, M palm plus M supernode. You get the end moment for the problem you are solving. And then you do the free body diagram, shear diagram, moment diagram, and then elastic curve. This is going to be a very long problem, so you must plan your work carefully, okay? So let us start by this problem, okay? This frame is what is unsymmetry, and then is subject to unsymmetric load. So for sure, the problem going to be the frame with side sway. It's going to be the frame with side sway. And based on this, the EI of the beam is 2 EI. The EI of the column going to be the EI. Okay, they are not equal. And this frame has the degree of indeterminacy to be fixed end, roller, so 4 minus number of equation of 3. So degree of indeterminacy going to be 1. How about the degree of freedom? Under the application of the force, I believe this is fixed, right? So this frame supposed to move to a new position, C palm here. So under this, I believe the frame will deform, okay? Will deform. Will have elastic curve like this. Okay, and then the degree of freedom that we have zeta sub A is 0, nothing. We will have zeta sub B, and also we have delta B, and delta B is equal to delta C. Say delta B is equal to delta C, since there is no axial deformation of the beam and the column. And then we have another one is going to be zeta sub C. So we have what? Zeta sub B, zeta sub C, and also delta for this problem. Can we reduce the complexity of this problem? Sure, because this one is the roller. So we will use 3EI over L for the beam. And we will use 4EI over L for the column. So 2EI supposed to put into this. This only EI supposed to put into this. Okay. So the problem from the analysis, degree of indeterminacy equal to 1, frame with side sway, and we can use 3I over L to reduce the complexity of the problem. And then from the principle of superposition, we will extend this beam from sidesway. Okay, by putting the roller, you just put the roller into the point B. When you put the roller into point B, this one will has the resistance force to prevent it from the sidesway. And then you may apply that force into the second frame. However, since you don't know, is delta is the unknown, you cannot determine the fixed end moment directly. You got to assume the fixed end moment. Okay, when you assume the fixed end moment, you will determine the M palm, and then you will determine the R palm. Okay, this is not the same as R here. That's why we have the correction factor to be R divided by R palm. And then when you finish this, you just do the modification C palm, M palm. Okay, and then you combine this one with the M supernode due to the applied, and that's going to be equal to what we are looking for, the end moment of the frame here. Okay, let us start by consider the first one. This is going to be the case 1, and this is going to be the case 2. By doing this, what we going to determine the K. Okay, this is going to be 3EI over L for the beam BC and 4EI over L for the column. Again, for the first one, we will determine M supernode and then unit R. And then for the second one, we assume fixed moment phi M palm and phi reaction R palm. And then we can determine the correction factor to socket. And then for the K, if we consider the K sub AB4 EI over L, it's going to be 1 EI. And this one 3 times 2 EI over 3. This one going to be 2 EI. That means the beam is 2 times stronger, or fractional have 2 times fractional rigidity compared to the column AB. Okay, and then the distribution factor for the fixed end is 0. For the lower end, or the pin end is going to be 1. And for this one is going to be the stiffness of the column EI divided by the summation of the joint stiffness EI plus 2EI is going to be 0.333 if possible. Put another 3 here. And the BC here, just 1 minus 333. And then you got this one to be 0.666 and 7. Okay. And now you're going to do the case 1 moment distribution. But before that, you got to find the fixed end moment. Find the fixed end moment for the case 1. You have very complex problem here. Okay, the equation is going to be very long one. I will provide this equation to you guys for sure. Okay, but you got to do the practice. What is the P? 10 kilonewton. What is the A? The A is going to be here. What is the B? The B is going to be here. The L is going to be L. Okay, L is going to be 3 meters. A is 2 meters. And B is going to be 1 meter. Put everything. Fixed end moment BC is counterclockwise. It's going to be negative. Okay, put everything like this. You get this one minus 4.44. Okay, how about the 10 kilonewton meter? You go back to what you had before. You just assume another member, just imaginary member, and then this 10 kilonewton meter going to act by the third law of Newton. That is going to be counterclockwise. This can be considered as the negative fixed end moment. Okay, and doing this external moment 10 kilonewton HIB is considered as a fixed end moment on the actual member, and it's going to be negative 10, like I presented before. And now you have the table is going to be A, B, C. Okay, remember A, B. A, B is here. Distribution factor here is going to be 0. Okay, and CB is here. And fixed moment here going to be 1. Okay, 0. And then this one is going to be 1. You should use 3. Oh, sorry, 4 if possible, because the calculator nowadays is easy to use. And then fixed end moment minus 4.444, and then minus 10. And then what we have is the equilibrium at point B. We has the 10 kilonewton and 4.44. The total to be in equilibrium, we require plus 14.44. Okay, we require it to have plus 14.44. Where is come? Just take this one up and it's going to come down here. Take this one up and it's going to come down here. When these two moments occur, 14.44 gone. So the choice B is in equilibrium. You get the moment M sub what? M sub BA, that's B, and A is over here, and this one must be carried over to this AB. So there is the carry over moment over here. How about the moment that's occur here? 9.63. Is it going to carry over to this? No, there is no carry over moment here, because this is the roller. Roller take no moment. Unlike this one, this is fixed support. It's absorb everything. So there is no BC to this one. No, that is no. Okay, and then this is going to be 2.41, and then you have all the moment at the end of the member of the frame based on the prevention of or no sidesway. Now we got to compute the R. Okay, based on this, your structure has what? Has the member, and let me draw the whole structure as before. This one is going to be C sub Y. This one supposed to be A sub Y, and this one is A sub X, is subjected to the forces here. And what we have, this is A. This is M sub AB 2.41. The 2.41 is here. And we are looking for what? We are looking for the force that prevent the sidesway R here. This R is related to the A sub A. Okay, by doing this, we just come to consider again for the column A, B. Okay, the column A, B here, we have 2.41 here. This is 2.41. Oh, it's clockwise, sorry. It's clockwise. The direction is not correct, it's clockwise. It's clockwise. It's going to be 2.41. It's going to be clockwise like this, 2.41. And then 4.81. Okay, 4.81 is here, is clockwise. This is going to be 4.81. The rotation like this will be balanced by the force of A sub X. A sub X must be in this direction. This is wrong. Just put this A sub X into another direction. Okay, it's going to be in this way. By doing this, you just take moment here. Summation of the moment at B equal to 0. So the A sub X can be determined by looking at this. This is 2.41 as I draw it. before, and 4.81 is here, and the a sub x, this one also the a sub x. You take moment about here, we have this one 4 times v sub a equal to the n moment. So you got this one for 1.805. This one could be 1.805 kilonewton. So the R, okay, you can see we can determine the R easily. Summation f sub x equal to 0, sorry. The R is going to be 1.805. That is the force that's required to hold the frame, prevent the frame from the sidesway. Now we move to the second part. This one we assume this frame to has this sidesway, and I should note that the beam has no deformation. Why? Because the beam has deformation from the previous case. This one is only due to the sidesway delta. Okay, due to the sidesway delta. And since we don't know delta, so we got to assume the fixed end moment. We assume the fixed end moment to be what? To be 100 kilonewton. And the fixed end moment that we assume has this rotation, has the counterclockwise rotation. So it's going to be negative. Okay, and then you assume this. Even though you assume the fixed end moment, you can use that assume fixed end moment to determine the delta. Okay, if you like to, you can find. This means you assume the delta for 266.67 divided by EI. This is assumed. Okay, if you like to find the actual one, you can find the actual delta. It's going to be C palm, and then it's going to be time delta over here. Okay, that is going to be the actual delta. That's we're going to find it later after we get the C palm. Okay, we will get the C palm. You got to find the R palm. Before we find the R palm, you got to find the M palm. We can't find the M palm. We put it into the table. Okay, now use the same table as before. Put the moment on the column AB. Okay, since this one has the sidesway like this, that is fixed end moment AB. This is A, this is B, and this is going to be fixed end moment BA. Both of them counterclockwise is going to be negative. It's required 100 to be in equilibrium at point A, and then time 0 and take downward here is going to be 0. Talking about the point B. Okay, the point B require another plus 100 plus 100. The plus 100 come from this one down. This one is going to be plus 33.3. Okay, and then this is plus 66.7. And now this 100 gone. Okay, it's gone. And then what happened is when you determine this, you have what? You have 33.33 in the BA, and then you can carry over this one downward here because this one is fixed. Okay, but on the other end for 66.7 you cannot carry over moment to here because this is the roller. Now there is no carry over moment, but there is a correlation here. It's 16.65. So you get all the end moment. Again, you come to this point and you come to the same frame, but now, okay, this frame has M sub AB negative 83.35. This is 83.35 kilonewton meter. Negative is counterclockwise. So the reaction that's occur for the roller here is going to be here, and then it's going to be convert here. Oh, sorry, it's supposed to be downward because it's going to opposite to the moment. Okay, it's going to be like this. And then this one, you will have this. This is counter clockwise. So the reaction for this one must be in this way. Okay, based on this, we're going to require the force. The force that's going to be what? To be the R palm. That is going to be the R palm. Before you can determine the R palm, due to this force, you got to determine this one for the A sub x again. You can determine this A sub x. You got to go back to the member, and you have what? You have 83.35 negative. And then you got this one for 66.7 negative. And then by doing this, you can see this is like this. So your A sub x must be in this direction, not this one. Must be in this direction. Okay. And then you are also in the opposite direction if this is to be correct. And now you take this. Okay. You are A sub x or V sub A palm here gonna be in the same one. So take moment over here. Your A sub x has this direction positive, and you have A sub x times the length of 4 equal to 66.7 plus 83.75. So you get this equation. You get the V of 37.51. What we have is this one is going to be the force of 37.51. So what you have for this one is going to be the R palm is going to be 37.51. So now you have R and you have R palm. So put into the correction factor, and you can see this is 0 equal to 1.805 plus this one must be C palm times 37.51, and you put everything together, you get the correction factor of 0.0481. Okay, and I always ask you what is going to be the correction factor, because this is important. The EI delta is going to be 0.0481 times 266.7. Now you get the correct size of the sidesway. By doing this is going to be M super O, and then you do the correction for the M palm. You sum this one by this one, and then you get this portion, and do the same thing for the author. And you must be notice. Okay, notice of what? Notice of the actual sidesway is going to be something like this. Now you come to what we have for the moment 1.61, 1.61. This one 8.40, and then you do the combination of this moment, 3 of them. You made the summation of the moment at B is going to be 0. Okay, and you are correct. And now you are ready to what? To draw the free body diagram, to draw the shear diagram, to draw the moment diagram. Okay, I supposed to finish for this example on the PowerPoint over here. Oh, we have one important thing. We're talking about the slope. Okay, after you draw this one, this is going to be the slope. When you draw the tangential line of this is going to be the 90-degree angle. This called theta B. You can determine theta B easily. You put the moment M sub BC over here. Okay, and then there is no, for the beam, there is no delta. And the fixed end moment BC, you have it already. Just put minus 4.444. And M sub BC is plus 8.40. Put everything together. You get this one is in the clockwise direction as shown over here. Okay, it's simple, right? And another example I will show you by writing it. We have this one in the PowerPoint, but I like to show you how to write it, because when you do the examination, when you do the homework, you require to write it into the paper. Okay, but anyone can go through this kind of analysis. Okay, this beam has the pin at A, has the pin at D. So the degree of indeterminacy, two unknown, going to be 4, minus 3 equation, degree of indeterminacy going to be 1. However, this frame, under the application of the force, the A can rotate, the D can rotate. How? Why you know it's rotate this way? Because 60 kilonewton push the frame in this direction. And then this one must deform something like this. This one must deform something like this. And then you have the sidesway of delta. Okay. And then this one must keep the angle to be something in this one. And maybe this one should hook like this and have this rotation. And then this one concave downward. This one concave downward. And the other, believe me, is will concave upward like this. So you have the theta A, theta B, theta C, and theta D. There are going to be total of 5. However, for doing the analysis of this problem, you will use 4EI over L here, and you may use 3EI over L and 3EI over L. Then the theta A and theta D gone. Okay, you can reduce the complexity of this problem to have only 5 degrees of freedom. Now, for the principle of superposition, okay, let me go by this. Going to be more simple. You may take a look at my work or may watch the video clip for my Thai class if you prefer the writing. And based on this, we will separate this one into 2. Another one is the frame with the roller. Okay, so by doing this, we can determine the fixed end moment due to loadings. Okay, from this fixed end moment, we can do the moment distribution to determine M super O. And then later, we will use the free body diagram and the equation of equilibrium to determine the reaction arm used to prevent the sidesway. Okay, and then this one must plus by another frame. Okay, by doing this, we are having the delta. So since we don't know the delta, we got to assume the sidesway. Okay, we assume the sidesway is not convenient. We must assume the fixed end moment. This time we assume the fixed end moment is going to be more convenient than you assume the delta that's occur over here. Okay, I mentioned this. If you assume delta, you got put into the equation to find the fixed end moment. If you assume the fixed end moment, you use it immediately. And then you just plug this one back into the M palm. Okay, and moment distribution and determine the M palm. When you finish determine the M palm, you find the R palm. This R palm is not real because it's from the assumed fixed end moment. We are going to find C equal to R over R palm. Where it's come from? It's come from this one. This is 0 equal to. This one is going to be R in this direction. and this one in the minus R palm. Since this one is assumed, that's why we put the C over here, and then you get this equation. Now, your M palm is not correct. You got to times the C by the M palm. And then this is going to be the correct moment due to what? Due to the sidesway. Okay. And you also can determine the actual sidesway equal to the C and times the delta as we do it before. Okay. And now, what we have is the moment here is going to be equal to M super naught here. And then plus this one. So we have this equation. And then you have the end moment of the frame. Okay. Okay. We have this one for what the problem should be. And let us go back. When we talking about the K, again, what should we do? This is going to be 3EI over L. 3EI over L, and this one is 4EI over L. So we have AB for the column, CD for the column. Let's say this guy is for the stiffness of the column, 3EI over 5. And another one is for the beam, is going to be 4EI over 6. Okay, this is going to be 2 over 3, 7 EI. And this one going to be 0.6 EI. Now, we move further. The distribution factor for this one, distribution factor AB is going to be 1. Okay, there is no moment here, is always distribute out. The same thing occur here. Distribution factor DC is going to be 1.0. And now we can determine distribution factor here and distribution factor here. They are equal. Okay. So distribution factor BA, and distribution factor CD. This is BA. This is CD. It's going to be what? Is going to be the stiffness of the column. This is going to be stiffness of the column divided by stiffness of the column plus the stiffness of the beam. So you get this one for 0.4734. However, when you compute these two also be the same. It's going to be 1 minus 0.4734. You got this one. Okay. And then you put into the table, and then when you put into the table, you get what you have. Okay, I will put it into the table and show you how to do it later. And then what we have is fixed end moment. There is only fixed end moment on the beam BC. Okay, that is going to be fixed end moment BC and fixed end moment CB, WL square over 12. So BC is going to be minus 72 and CB is going to be 72. Okay, and for the column, they are 0. Let me put everything into the table, and I will show you over here for the moment distribution to give you more in-depth on how we do the moment distribution, since it's important to do so. So let us consider, we have what? We have this one for pin. This one going to be 1 point. Oh, the joint. We start from the joint A and B. Let me do the correction of this table. This is going to be B, and then C, and then over here D dot, and this one going to be what? A, B, and this one is going to be what? B, A. Okay, and then you go further. This one going to be B, C, and this one going to be C, B. Okay, and then this one going to be C, D, and the last one is going to be D, C. Okay, and to make it correct, this one also must be 0. And now you have what? You have this one. If you remember this one, they are equal 0.4737, 0.4737, and the other one that we have for the blue, that is 0.5263, okay. And then what we have is the fixed end moment. The fixed end moment has over here, this is going to be the fixed end moment BC. BC is here, okay, and this is counterclockwise 72.0 if you remember, and this one going to be plus 72.0. I do this because I like to show you how to do the moment distribution. For the first one over here, okay, you have 72.0, and then for this you require is for positive 72. Positive 72 times 0.4732 is going to be 34.11 plus 72 times this one is going to be plus 37.89. okay, this imbalance, some of them are 0. And then a little bit further, you require this one for the negative 72. That time this is going to be 37.89. Negative 72 times 0.476. That is going to be negative 34.11. Okay, you have this moment to be over here. 34.89. This is going to carry over here, 37.89 positive, and this one negative 37.89 is going to carry over. So we have carry over moment that occur in the beam. Okay, there is no carry over from here to the pin. No, there is no carry over to the pin, only this one. So this one will reduce by a half. This one positive, this one negative 18 divided by half, 0.95. This one 18.95. Now for the second round, we come into this one negative, right? So we require to have it in the positive 18.95 times this one, you will get it for 8.98. 18.95 times this one, you will get it by 9.97. And then come into this portion, this is plus, we require negative. You use the same thing, 9.97, 8.98. So it is in equilibrium. Okay. Then the third round coming into this going to provide you the negative, and this one is positive. Okay. And then you divide this by half. It's going to be 4.98. It's going to be 4.98. You do again for the equilibrium of this. It's going to require you to put the positive, and for this one is again to require you to put it in negative. If you notice what I'm working here, you use the color coding. That's going to help you. Okay, this one time this one, you get 2.36. This one going to be 2.36, and this one going to be 2.62. Okay, this one minus, sorry, 2.62. This one 2.62. This one 2.36. And you did everything until you finish. You will get this one to be 0, 0, because it's the pin is always 0. And this one going to be plus 46.28. This is minus 46.28. They must be in equilibrium. This one 46.28. This is minus 46.28. Okay, and now you what? You got to go back and consider your structure. Your structure is what? Your structure is less 10 from the what? The side sway. You structure pin here and pin here. Okay. Application of this one is going to be 60 kilonewton. And what you did before, you put the roller over here, and you must have the reaction here. And what you compute now, you get the moment. Okay, the moment here is occur on this one, and the moment here is occur on this one. What you have is going to be this A, B, and this one is M sub BA 46.23. This one positive, this one 46.28, sorry, kilo Newton, and this one you also has the column, but it's going to be D, and over here C. You have this one is minus 46.28. This is going to be 46.28 kilonewton meter. And you can see, due to this one, for sure, the force occur here, let's say it's going to be AX, okay, and this one going to be the DX, and this is due to the moment. There is no moment over here. It's 0. So your summation moment at point B equal to 0. Your A sub X is going to time this one for 5 meter. Okay, and then it's going to be equal to 46.28 now. You're going to have the A sub X equal to 46.28 divided by 5. That means you're going to have this one for 9.256 kilonewton. And since this one is the same, this one also 9.256 kilonewton. And then what we have is this one and this one. You have this one 9.256 and this one also 9.256. So summation of X sub X equal to 0. Positive is like this. R is a positive, and then plus 9.256 minus 9.256, and then is minus 60 kilonewton. So your R of this one is going to be 60 kilonewton. Okay. Now we move to this second portion. You're going to assume, if you go a little bit further, you're going to assume the frame to be sidesway, and you're going to put the frame into another position. It's going to be like this. It's going to be like this. So for this one, you got to assume this fixed end moment. This is going to be fixed end moment. This A, B, C, D. This end moment C, D. And this is going to be fixed end moment BA. Okay. You may assume it, and then you put it into this position. You may assume fixed end moment BA, and that is equal to fixed end moment CD, and that is going to be counterclockwise, right? So 100 kilonewton meter, and this one gonna be BA minus 100, and another one is CD is here minus 100.0, and now you going to do the same thing over here. There is the unbalanced moment. You need require to have plus, okay, plus 100. Okay, you go over here. The first one going to be plus 47.3, 100 times this, and 100 times this plus 42.63. Okay, and then you come into this one, you require plus, okay, the same as before, plus 100 times this one plus 52.63, and 100 times this one is going to be plus 47.36. So you finish the first one, and then you may do the carryover moment. Then what we have to for the carryover moment is going to be reduced by a half, 26.32. This one 26.32, and now you require it to be in equilibrium. It's going to be negative, right? Now it's going to be negative, and it's going to be negative. This one time this one, you take it to be 12.47. This one time this one, you take it to 13.85, and then you got this one, sorry, 13.85. You copy the same. This one 12.47, and now this negative, and it's going to reduce by half, 6.93, and then you do the same thing, okay, to make it to be in balance. This is negative, so it's required positive. Do the computation. This is going to be 3.28. This is going to be 3.64, and this is going to be 3.64. This is going to be 3.28. You do the same thing until you finish. This one going to be 0. This one going to be 0. You got this one plus 62.50 minus 62.50, and for this one you get it minus 62.50 plus 62.50. What we have is going to be in parallel to what I show you over here. You take another frame now over here, and this frame, what we have going to require this palm, okay, and this one is going to be fixed. What we have is determine the A sub x and also the D sub x. You will determine this one. You got to do the same thing as before. You use the free body of the column. This is A, B, like this one. This is D, C. What we have is the again, this one minus 64.50 is going to be minus, okay? This is going to be 64.5 kilonewton meter, and coming into this is also has the minus again. This is going to be 64.5 kilonewton, and for sure, due to the rotation of this one, the force over here must be A sub x,
and this one also must be d sub x, and your summation of the moment at c equal to 0. Your d sub x gonna time 5 rotate in this direction, and it's going to be 62.5. So your d sub x going to be 12.5 kilonewton, and this one also going to be 12.5 kilonewton. So this is 12.5 kilonewton. This is 12.5 kilonewton. Okay, and then you do the summation of x sub x equal to 0 in this direction. In this direction, so your R prime is going to be 25.0 kilonewton. Okay, and then we find that C, okay, equal to what? Equal to R divided by R prime from the equation that we have before. That is going to be 60 divided by 25 is going to be 2.4. Okay, and then you do the correction of this time 2.4 times 2.4 into this one, and finally you get this one for minus 104 plus 104 plus 196 minus 196. What we have here is similar to is in the PowerPoint. Okay, please go to the PowerPoint. Let me show you a little bit. Okay, so this one, so what we have from the table, the same thing, and then you compute to get this R to be 60, and then you come to set the fixed end moment for this one to be 100 negative. Okay, and then you can compute for the delta part if you like. This is assume. Okay, assume delta part is not correct yet, and then you put everything into your table. The same thing, you get this result 62.5 minus plus and minus. You do the same computation, you get R prime equal to 25, and then the correction factor C prime come from what we have here 60 and 0 equal to 60 minus 25 times C prime. So C prime is going to be 2.4, and then you put everything together. Okay, do the correction for the N prime. You times 2.4 with 62.5, you get 150, and then you combine the first row 42.18. Oops, sorry, 42.18 with the what like this. Okay, you get the end moment, and end moment AB is pin, DC is pin. That is correct. And also the summation of the moment at B must be 0. The summation of the moment at C must be 0. Okay, I should put this one at B equal to 0. Summation at C equal to 0. You must check it, and then you go further to draw the shear diagram, moment diagram, and also you can determine the reaction and axial force. This is axial force, and draw the elastic curve. Okay, next time I will come to the problem with the frame of unequal column.